I hope by now you would have already understood like what are the different principles behind principle based on which the entire subject of engineering mechanics will be working. So we have come across already the principles of physical independence of force, the principles of superposition of forces, and finally the principle of transmissibility of force. So I hope you have understood this. So we also came across what are the different Newton's laws of motion. So based on this, the entire Newtonian mechanics is based on this principle, which gives the laws of motion. So any rigid body under consideration under motion will be following all these three motions laws of motion. So based on which we will go on further. So today, like in today's class, we will just see what are the different aspects in mechanics that is very much essential to solve real life situation problems. So today we will see how we can resolve a force into its components, and we will see what is meant by composition of forces. We will also see what is meant by a resultant of forces, and we'll also try to solve a simple problem on this concept of resolving. So you must have a prerequisite requirement of some trigonometrical knowledge. So based on that only we'll be following this particular concept of resolution of a force. And then following that, we will just have a look at how to develop a free body diagram when you're posed a question in any the how to actually realize the diagrams what are presented in your concept in the subject of engineering mechanics. So we will just browse through all the areas which I have listed in the description of this today's class. Start with, we will just see what is meant by a resolution of a force. So in resolution of a force, you might have already seen this in your mechanics in the physics, what you have studied in secondary schooling. So there, the process of splitting a particular force into its components, we call it as resolution of a force. So basically, generally we divide this or resolve this particular force in two directions, that is x direction and y direction. If you're talking about a Cartesian plane, so you can see here, if a force is acting along from a particle called O here in this case, so it is originating from O along this direction at an angle of theta degree from the x direction. You can resolve this particular force in along x direction as well as in y direction. Here you can note that you are resolving the force into a mutually perpendicular axis. So you will be resolving this particular F force into an x direction and y direction which is mutually perpendicular to each other. So this is what you'll be doing in the entire subject of engineering mechanics. So basically you work everything in terms of a horizontal and vertical direction, that is x and y direction. So from your basic knowledge on trigonometry, you know that if the adjacent side of the angle, whichever you know, you can call it as the cosine component. So the magnitude of the force will be along the adjacent angle. You can call it as f cos theta. You get the value as a f cos theta, where theta is the angle between the force and the axis. Whereas the mutually perpendicular axis, whatever the mutually perpendicular axis, whatever it is, you can get the value of the force in terms of f sine theta, where theta is again the angle between the force and the adjacent component. So I hope you have studied this, the basic knowledge in trigonometry. That is actually when you make a triangle like this right angle triangle, you can see what is sine theta, what is cos theta, and what is tan theta. So from that, actually this particular thing is derived. So you can work it out again and just check it whether if it's right or not. So basically, the better for a easy understanding, we make it something like, if the force is this is the force and this is the angle. The adjacent side of the force, whatever the angle is known, we call it as the cosine component, and the mutually perpendicular component, we call it as a sine component. So on the similar grounds, if you can call the process of splitting of a given force into its components as a resolution of a force, we can call it the other way also, like the process of merging two known forces into one force when the angle is known, we can call it as the composition of forces. So you can combine two forces also when the angle is known to you, provided that the angle are the angle between two forces is 90 degree. Yes. I hope you have understood this resolution of a force. You might have already seen this in your mechanics, which you had undergone in physics stream in the secondary schooling. So this is regarding the resolution of a force, and we will just see what is meant by resultant of a force. So this is somewhere related to your basic principles of engineering mechanics. So we will see how this works. So basically, if a number of forces are acting simultaneously on a particle, say for example, this is a particle under consideration. So what is meant by particle? You have already seen this in the previous class. What is meant by a particle?
Which
Yes,
has
anyone?
no
Yes,
shape.
yes.
Has only but no size.
Yes, the particle has only mass but no size. So consider this as a particle which has no size here, since although I have shown it in a bigger format, consider that this is not a size. So you can reduce it to an infinitesimally small size which has only mass. So which has a mass, which will be exerting a force in terms of self weight. So that is represented as W, and there are many other forces like F1, F2, F3 acting on this particular particle. So considering this scenario, you can resolve all the forces whatever is acting on this particular particle and come up with a resultant force. So by how can you achieve this particular resultant force? How can you find this resultant force? Yes. By the basic principles of engineering mechanics, from the whatever knowledge that you have now, how can you find this resultant force? You have all these forces. How do you arrive at this force?
Net force.
Net force, yes. But how will you determine this force? Because here in this case, all the forces are acting in different directions. So how will you get to know this force? The resultant one. So basically what we do is you resolve the force, whatever is known to you, you will be resolving it in X and Y axis. So find out the component in the Y axis, find out the component in X axis, again do it for F2, again do it for F3 and W. After that, just it's an algebraic sum, like your principle of superposition of forces. So you will get a resultant force which is acting what does the resultant represent? That means to say that the resultant of forces is actually representing the net effect of all other forces on the single body. So you can what I mean is, instead of having say for example 1, 2, 3, 4 forces are acting here and it is acting simultaneously, you can resolve and get to know that what is the final effect of this force individually, what is happening. Say for example, when F1 is acting on the body, it is moving in this direction. When the self weight is acting, it is moving downward direction. F2 in this direction, F3 in this direction. So it is equivalent when all these forces are acting together. What is the net effect is happening? It is equivalent to what is the net effect happening with the resultant force. Yes, that is the basic principle of engineering mechanics that you have seen from superposition of forces. Same thing is again here, like in that particular sense, what we have spoken principle of superposition of forces. And in actual sense, the principle of superposition forces will define the meaning of what is meant by a resultant of force. So basically, a single force which will have the same effect as the system of forces is called as resultant of system of forces. So the same principle is again, sorry, the principle behind this is actually dealt in the principle of superposition of forces. So are you getting it? Like basically you should understand here how to get the resultant of force. Yes? Are you understanding?
Yes, sir.
Yeah, okay.
Yes,
So
sir.
thank you. So you can just try it here that I hope you're taking down the notes. So you can just try, say you have a point here and from this particular point or a particle, there is a force acting in this direction of approximately magnitude of 160 kilonewton, and the angle with respect to the horizontal or the X direction is 20 degree. So you can just resolve this particular force into their x component and y component and just tell me the values that you are getting along x direction and y direction. And I hope I think during your secondary schooling, you are not supposed to use a calculator, right? As a scientific calculator. So here you can use that. I hope most of you already have the calculator. Do you have the calculators with you? Hello?
Not yet, sir.
Not yet.
No,
It's
sir.
already you're already late because you are supposed to have you buy a scientific calculator immediately because it is actually essential from day one of engineering. So you get the calculator immediately and you start using because it's unlike your secondary schooling. You will not be using your log tables or calculation tables anymore. You'll be directly using your scientific calculator for all calculation purposes. So just purchase it as soon as possible. So you should be well versed and know how to use a calculator. You should be expert in that. So you buy a calculator immediately. So probably you should buy a FX model with the 991 MS or ES. You can note it down. So MS, it can be MS or ES. I hope you know the brand, right? You know the models. You should be knowing the models by now. Hello?
Sir.
Yeah, you should be knowing the models by now because most of the subjects which are taking by now should be using calculators by now, right?
Yes, sir.
Yes,
So
sir.
at least is there anyone who has a calculator with them?
Yes, sir.
Yeah. So are you getting the solution? So basically, I told. See, this is the resolution way. So basically, if the force is known and the angle is known, the x component will be the f cosine of the angle. So that is f cos theta, and the y component will be f sin theta. So simple calculation. Just type in the values. Are you getting?
0.93.
0.93. 0.93. Who is that? No,
Cos
no, no,
20,
no.
sir.
Cos 20. No, no, no. I'm not asking about cos 20. I'm asking about the x component and y component. So if this is F, that is
Sorry,
160 kilonewton, the x component should be F multiplied by the cosine of the angle. So it will be 160 cos 20. And it will be around
Sir,
160 cos 20.
sir, 150 answer.
Yeah, it is 150.35 kilonewton.
Yes,
Yes,
sir.
I'll just write it down. So it is 150.35 kilonewton. So this will be 160 sine 20. So that will be 54.72 kilonewton. So this is it. So you can resolve this particular force into two components, that is along x direction and y direction, and you can arrive at what is the value that you can get along the x direction and along the y direction. This means to say that from this particular problem, you can analyze that it is equivalent that if you apply a force along this direction along 20-degree angle at 160 kilonewton magnitude, if you pull this particular particle here, it will give the same displacement as applying two separate forces along x direction and along y direction of these magnitude in the at the same location, at the same point. So displacement will be common. So the effect will be same, so that the intention behind resolving this particular force is this will make us easier to analyze the difficult problems. Like in this case, it's only one force. So if you are having multiple forces, say for example in this case, and you want to know the resultant of the force, this is F. In this case, it will be very difficult to analyze what is the resultant force if you are having multiple amount of forces. So that's the reason why we are considering a resolution of a force. So maybe we can just try the same system of forces here again. I'll just plot it here. So we have the same system of forces. I'll just put it here, and this will be a resultant force. So I am removing it. You just find out the resultant force for this. I will just give the angles, the horizontal angles. Just a second. So say this is the x-axis here, and the angle here. The angle here. The angle here. Yes. And this will actually be difficult, so just I'll just make it easier. So since we have taken as a particle under consideration, I've just reduced the size of the particle and just made it easier for you. So okay, now let us see. I'll just give the values for the angles. Just see how you can resolve it. Say for example, this is 60 degree, and this is say 65 degree. And this is again, I'll make it 60 itself. Very complicated. Okay. Yeah. Now just resolve these forces individually. Make it individually. Like make it simple. Yeah. You just generate like F1 along x-axis and y-axis. Just you can just what you can do is make a table and just resolve F1, F2, F3 and W. Make the y component separately and keep the x component separately. And sorry, you should have the values also, right? Yeah, force values also should be known. So I'll just give kilonewton. 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 It is yes. So go ahead, just evaluate this and just let me know what are the solutions you are getting. So I just gave 60 because that will be easy for your calculation. So your cos 60 is 0.726 and sin 60 is 0.866. So basically, when you're when the thing you should make a note of it is whenever you get whenever you are using a calculator, you should keep your angles, whatever the angle settings, to be in degrees. Make a note of this, because the calculator has a setting of maintaining the angles in degrees as well as in radians. So make a note that in most of our cases in engineering mechanics, we'll be using the angle in terms of degrees only. So each time you use a calculator, just reset it to degrees and then start working. Yes. Are you getting anything? Are you getting to solve the problem? Are you able to resolve it into different axes? See, this particular problem may not be in equilibrium, but as this is just a random numbers that I have given just to evaluate, just to see, like if you are able to get the practice of solving it. This is not in equilibrium, but I can understand from the figure itself. So it won't be equating to 0. Doesn't matter. Yes, can just anyone tell me one by one what are the resolution forces? F2, F3, and we have W.
So F1 X
F1 is? Yeah.
F1 X 4.2.
X component is 4.2. F1 is 10. So 10.
Y component 9.06.
This 9.06.
063.
Wait. There is something. F1 is 10 cos 60. 10 cos 60 should be, it should be 5, right? Why is it 4.2?
Sir, I took 65 degree.
Okay,
So
fine.
8.6
Yeah, how
y
much is it?
component.
8.6.
8.6.
Okay, fine. Yeah, I just changed it to 60. So just make
Yes,
it
sir.
right. Yeah.
So F2.
Yes.
X component 25.
Y
25.
component 20.
25.
Y component is also.
14.
20.
Sorry, I'm not able to hear you.
So 43.30.
0. Okay. F3.
So F3. X component
Yes.
50.
X component is 50.
So Y component minus 86.60.
Minus 86.60.
60.
Okay.
So there only. So F1 minus 5.
No, I haven't taught you regarding the sign convention yet. So just wait. Okay. So
Okay.
W is
Okay,
again,
sir.
there is no X component. There is only 0. And this is 40 kilonewton. Okay. So this is how we resolve the forces. That is regarding like how we can simplify the given problem into X component and Y component. Keep all your forces in the known X direction and Y direction. That's how you can work on using the resolution of forces. Now, as who was that? Who told the sign convention? I could not see. Who was that given the solutions just now?
Sir, me Yellapa PG.
Yelapa, okay, fine, thank you. So as Yelapa told that the angles, the sign convention is also of very important because in order to solve this particular problem, if this particular problem is actually in equilibrium, if this case was in equilibrium, you can come at a resultant force directly. So still this is not in equilibrium, so that's the reason why I'm not asking you to solve it. So the basic convention, like your xy Cartesian plane itself, you have to follow this basic sign convention. I will just give the convention here. So you're in the first quadrant, so whether it's x or y, both will be in positive direction. So in second quadrant, x direction will be negative, y direction will be positive.
Yes, sir.
Negative.
Yes.
Here it will be negative. Yeah. So this is a sign convention that you have to follow. So anything in this case, once the F3 level. So you have seen the principle of transmissibility. If the particle is here along this particular line, wherever the force acts, it's the same. So you can have F3. It's equivalent to say that this particular thing is acting here itself. Sorry, since the angle is same, it will be here this way, and this particular F3 is acting here. So the first step of your resolution will be in this case. So F3 is acting at the same point, 100 kilonewton. Resolve it again, you will get the same solution. So since this one you are resolving, you are getting in the negative x direction. The x component will be in negative sign. So this here F3 will be negative. and F1 will be negative. And yes, so what else? F2 both are positive, fine. So this way, yeah, if you have any doubts, you can ask me regarding this, this resolution of force. So do you have any question? Anyone who has solved this problem, you can, if you have any doubts, you can ask me. So if you don't have any doubts, I can move on further. So this is how we resolve the forces. So we'll have some more concepts to be introduced before starting the actual numericals. Some of the law of forces, that is parallelogram law of forces, polygonal law of forces, triangle law of forces, all these things that we will take up in the next class. Before moving to the next class, like topics like that, I just want to introduce one more topic, that is generation of free body diagrams. So I'll just share the screen with you now. Just tell me if you can see the screens. Yeah. Do you have the visualization of my slide?
Yes, sir.
Yes, sir.
Okay, so basically the free body diagram is very important, because in order for you to get such a diagram, like whichever I have given you, like a force system which was shown to you, to understand the real world scenario and to convert to such a kind of diagram, the free body diagram helps you. It's actually a diagram of a body which a body under consideration is free from all contact surface and shows all the forces acting on it, including the reactions from other bodies. So say for example, I gave you example of that ladder, person standing on a ladder. So the diagram which I showed you in the left side, that is which I created, I showed the floor, then the wall, then the ladder, then the load acting on it, and what are the force exerted on the wall as well as on the wall and the floor, and then what are the reactions that were exerted by the wall and force on the ladder. All those things we have seen. So that is actually called as free body diagram. So wherein you will be showing all kind of forces which are acting on the system alone. We are not bothered of who is standing nearby, and if it's a person or if it's some kind of a weight. No, all those things are neglected. You just as you've seen in the basic idealization of mechanics, as well as from the basic principles, what are the components required, and if you are talking about a force, what are the characteristics of the force. All those things should be defined. That is the magnitude of the force, the direction of the force, the line of action of force, as well as the, what's the other one? Yes, the position of the force, that is at what distance that particular force is acting. So if those parameters are known to you, you can easily create a free body diagram. As you can see here, this is again the same thing represented. So you can see a person is standing on the ladder. So this particular scenario is again converted into a free body diagram here. That is the length of the ladder is known. So we know we'll just place a ladder here, and then find the wall, instead of a wall and floor and all, we'll just keep the reactions offered by those particular bodies. Say for example, in this case, this is the place where the person is standing. So you'll just convert the entire body weight of the man into a point load. So he's standing on a point at this particular location, like almost 3 meters away from the floor. So along this direction, almost 3 meters, he'll be standing. So there is a load acting here. So you should be knowing what is the magnitude of this particular force. And then there is one more thing, that is the self weight of the ladder, that is acting exactly at the centroid or center of gravity of the body, at the center, and that will be acting in a downward direction. Other thing is at what angle that particular ladder is placed. Even that is very important, because that is a direction that shows the direction of the force, how it will be acting, and that is also essential for resolving the force. And then there are two forces acting. These are the reactions actually. Reactions from the wall as well as from the floor, what is acting. And there is, since the person is standing over here, there will always be a frictional force acting in along the opposite direction. So these are the system of forces acting here. So you can just see, you can consider these as a coplanar force acting in the same plane. but they are not parallel. They are not collinear. They are not concurrent. They are only a coplanar system of forces. So this is how you generate a free body diagram. So we will just give a few other examples also. You can see here. Here in this case, a ball is lying on a floor. Or this actually the shaded region, or a line and a shaded region actually represent a smooth surface. So you can see if this particular representation is done, it means that there is minimal friction. You can say that frictional force is 0. If at all there is a friction, the arrow mark and the frictional force will be mentioned. So in this case, you can neglect the frictional force, and the body, particular ball is resting on a smooth surface. In that case, the self weight of the ball will be acting in the downward direction. In return, the floor will be offering a reaction in the opposite direction. That is actually represented in the free body diagram in this way. Like there is a ball here, and the weight is acting in the exactly downward direction, and the reaction is also acting in the exactly opposite direction. So there is another example where a ball is tied to the wall, and the ball is in rest onto the smooth surface, or on the smooth surface of wall. So in that case, there are 3 other forces. That is, one is the self weight of the ball acting downwards, exactly downwards. And since this particular ball is resting on the wall, there will always be a resultant, or a reaction from the wall exactly perpendicular to the ball. That means in the R direction, as you can see here. So as exactly perpendicular to the wall, there will be a reaction acting onto the ball. That is exactly represented as R. And then since the ball is tied using a string, or a thread or something, so the self weight, the reaction of the self weight will be acting along the direction of that particular thread. That is represented as T. So this will become the free body diagram for this scenario. So you should be in a position to generate a free body diagram for any case that is given to you. Say in this case, there is a ladder again. So here we will just see what are the forces acting upon. So there is a weight acting here. There will be a reaction from the wall. There will be a reaction from the floor. There will be a self weight of the ladder acting downwards. And again, due to frictional force, there will be some kind of force acting, that is represented as P. So that is regarding the ladder scenario. And again, when you're talking about this kind of a pulley arrangement, so you might have seen this kind of arrangement like a pulley, like the weights, both the weights will be balanced using a pulley. So in this case, we can see in this case, the weight of the body, that is 600 Newton, is added here. Wait one second, I'm not able to. Okay, yeah. There is a 600 Newton of weight, and it is balanced by a 400 Newton of there is some there is some confusion here. Block weighing 600 Newton. Okay, fine. This is actually a pulley where 600 Newton is pulled. In that case, the 600 Newton will be acting in the downward direction, and the tension will be acting along the thread, whichever is there. In this case, the consideration is only about the 600 Newton. The point of focus is only on 600 Newton. The 400 Newton is not considered. So the 600 Newton is lying around here on the floor. The 600 Newton is weight, and the 400 Newton is weight is actually handled to balance the 600 Newton force. So there will be a tension here. So that tension force is actually calculated as T, shown here as T. The self weight is 600 Newton, will be acting downwards, and there will be a reaction from the floor, which will be acting exactly opposite direction of the self weight. So this is how the free body diagrams will be generated. So the first step in solving any kind of problem, any kind of such problems, will be generating a free body diagram. So we can see more examples are shown here. One is various engineering components where you can see the body bell crank supporting mass M with a pin support at A. So there is some kind of arrangement here where there is a bell crank supported by a mass at M with a pin support at A. So in this case, how can you generate a free body diagram? This is actually incomplete free body diagrams. So you can see here the mass should be converted into weight. You cannot keep all the weights. You cannot keep all the mass values because it should be converted into newtons. Even if in case some kind of values are given in terms of kg, you are supposed to convert it to Newton and keep it for solving the problems. So in this case, the weight is acting on the downward direction, and the tension, like this is a bell crank, so there's a tension member here. The balancing act is done by the bell crank and this particular tension member, or a flexible cable in this case. So a tension force will be acting along the opposite direction, and there will be since this is a support, so there will be actually in this case there will be two reactions. One is acting directly upwards, as well as in the x direction also there will be a force. So while creating a free body diagram in this way, you should be in a position to identify in what directions the forces are acting. So even in this case, say for example in this case, the x direction or the x component is not added to the system, you will lose actually a major component which is not considered. That's the reason why it's called as incomplete FBD. So horizontal force also should be included in this case. So the user has not added that particular horizontal force here. That's the reason why we call it as an incomplete FBD. Because in case this particular horizontal force is added, and even after resolving all the forces you get it as 0, never mind. That means that you have considered a force, but there is no force exact force acting on it. But still, you can see here it's not in a perfectly 90-degree angle, and there is a tension member here. So obviously there will be a horizontal force acting here in this direction, which is not considered. That's the reason why we call it as an incomplete FBD. So there are many examples. I will just deal it with in the upcoming sessions. So I'll just deal it with exact problems which we'll be solving. So coming to a real life scenario, say for example you are standing in a lift. Can you identify all the forces that are acting on this particular member in the lift? Just make a free body diagram for this. So obviously you are going upwards in the upward direction. So assume that you are the only person standing in that particular lift. So can you just draw a free body diagram for that? And let me know how many forces are acting.
So 2.
2 forces.
3 forces.
Sorry, I didn't hear you.
3 forces.
3 forces. Any other answers? Any other answers? 2, 3. Okay. See, here is a solution for your answers. So in the free body diagram, like basically when you build a free body diagram, you are supposed to have a reference axis like x-axis and y-axis, and then the self weight of the body, or you can call it as a self weight of the person, as well as self weight of the containment unit, whichever you are thinking of. That is one. And then the tension member, like whatever is acting in the upward direction, the reaction, what is happening in the tension member. So these are the two forces that are acting. Mainly, if you're considering weight of a person as well as weight of self weight of the cabinet, that will become 3. So basically, there are 3 forces. But still, if you consider the weight of a person as well as weight of the cabinet together, you can call it as a weight force acting towards the downward direction. So, do you have any other opinion? Like, I think this is what you told, right? Like the person who told 3, it means the self weight of a person as well as self weight of a cabinet. Or is it anything else that you have considered?
No, sir.
Yeah, fine. So you basically took the self weight of a person as well as self weight of a cabinet differently. Okay, so this is how this works, how the free body diagram works. So this is a way how you need to build a free body diagram. You should have your reference axis shown properly, and if there is any particle or a rigid body under consideration, even that has to be shown properly. And the different, as I said you, like in the beginning classes, what are the requirements of force that has to be mentioned while indicating the force? That is, along the direction of the force, you need to mention you need to denote like what is the magnitude of the force as well as the direction using an arrow mark, and then you need to give the reference axis, that is x and y direction, and if you are resolving it, you need to mention it as a resultant force. So these are the basic requirement for developing a free body diagram. So we will just look into different problems and different laws pertaining to these force systems. I hope now you are clear with all the basic principles and basic idealizations that are made in this particular engineering mechanics. So from next class, we will start analyzing some of the laws, and we will start solving some problems. So majority, like almost 4 classes we have spent discussing about the theory behind. So we will start solving problems from next class. So just make sure that everyone is having a calculator. I hope we'll start having the offline classes very soon, because this is actually very difficult to solve this numerical problems online. So I hope it will start as early as possible. And then ensure that almost everyone, not almost, everyone has a scientific calculator with you while solving the problems in class, and solve the problems along with me, like you do in your regular classes. So solve the problems along with me, so that will make you perfect, like you'll get a practice of solving those problems. So this particular subject is majority of the subject is involved in numerical problems. So make sure that you practice a lot of problems. I will be definitely solving a lot number of problems by referring to different kinds of textbooks. Still, if you get a complication in any problem that you are solving by yourself, please get it to me. I can solve it in class. So yeah, regarding if you have any doubts, you can ask, or we will just wind up the class today. Okay, any questions? Okay, fine. Then I'll do one thing. I'll download the attendance, and then you can leave. 1 second. Yeah, okay. Yeah, I have downloaded the attendance. So if you have any questions, you can ask me. Else we can wind up the meeting today. Okay, I think the attendees are very less in number, 16. Okay, out of 40, only 16 have attended. Okay, yeah, fine, that's okay. Okay, thank you then. We will meet in the next class. I hope we have the next class on next Monday only, right? Yes.
Yes, sir.
Yeah, okay, fine. We'll meet in the next class. We'll start solving problems in class. Ensure that by then you have a calculator with you. Okay, thank you.
Thank you, sir.
Thank you.
Yeah, you're welcome.
Thank you, sir.
Thank you, sir.
Yeah,
Thank you, sir.
you're welcome.
Thank you, sir.